All right. So today I decided to give you guys a little surprise and start off something new. We'll just stall this whole discussion on motions for some time. And then now, after 2 days, when I revisit it, you're going to feel good because you know exactly what is causing these motions. Okay, so today we're moving into what they call the laws of mechanics. Also often referred to as Newton's laws. In fact, what we're discussing for the last few days, motions, and now we are moving into the laws of motion, which means we're going to discuss causes of motion. What caused the motions that we've been studying in our chapter of kinematics? Whether an object was moving in a straight line or it was taking a parabolic kind of trajectory, or it was moving in a circular motion. Now we are interested in finding out what caused these motions, the causes of them. And it is now that we really are launching ourselves into what we call mechanics, often referred to in books as Newtonian mechanics. And some books refer to it as classical mechanics. Well, Newtonian mechanics, that's good because you will soon find that all the laws, these laws of mechanics, laws of motion, etc., they were all derived from the core relationships that Newton gave. Soon you will find that we will move into chapters which talk about work energy, or we move into areas where we are trying to understand collisions, where there's an impact, impulse, or where there is a change in momentum, etc. These terms which I'm using, they all were derived from the Newton's laws. And hence, the entire mechanics that we discuss is often referred to as Newtonian mechanics. What do we discuss here? We discuss the dynamics of rigid bodies. Dynamics. This is a chair in front of you, and if I give it a push, this is a dynamic situation now. The chair is being pushed. That means there is a force involved, and its position is changing. And we say this whole situation is a dynamic situation. You understand? The dynamics. And why rigid bodies? Well, as I explained to you in the very first few classes, that there's no object on Earth which is rigid. There is no object on Earth which is rigid. This metal or this board, ceramic board, which to touch appears to be really solid, you can't penetrate it, etc., etc., etc. If I were to look at it at a micro level using a very sophisticated microscope, then I would find that as I push in, there is a deformation. The boards seem to be going through some depression. Every object which appears to you as solid is really not so rigid and solid. It has certain element of elasticity in it. All objects around us. My hand shows a great level of elasticity. I'm applying a force, but my hand is not moving. What's happening? There's something else happening. The object is getting deformed. Its shape is changing. And when I withdraw this force, it comes back to its original shape. But there was no motion. You see that? Yes. Now, this is a very sophisticated discussion. It can only be discussed maybe after 6 or 7 chapters, because we have to understand this term called elasticity. But then Newton had a short way of explaining it to you. He said, all right, you don't have rigid bodies in life. Everything around us has some element of elasticity. Every object around us can be deformed. And so he says, but my laws, which I have created, are only for rigid bodies. It's a very idealistic situation. So what do I do? So Newton said, I had an object which had some element of elasticity. So as a symbol, I represented this object with this section, some rectangular section, which basically means it's a block, but this is just a symbol. This represents this guy. Tomorrow it will represent a chair or a table or a football. It's a symbol of representing a rigid body. But it had some elasticity. So he says, since my laws apply only to rigid bodies, so I remove the rigidness of that object here, and I separated out the elastic component from it. There. Now, this entire object is represented by this symbol. There is a rigid part of it, and there is an elastic part of it, a spring. Both these together make up this. Understand this whole context of things, because you'll suddenly find books having a block and there is a spring and all kinds of situations which the examiner creates, but in real life you never see. I've never seen a person walking with a spring hanging behind it. Have you? Nobody's seen. So be practical in life. Try and find out, why is it that the examiner or the book author is making me, or that physicist is making me study objects with a spring? A spring is something which we all generally have experienced, where you can deform the spring, correct? And when you release it, it comes back to more or less the same state. This represents the elastic property of this material. And this is the rigid part of the object. Please understand this, because your teachers never tell you that, and they'll take a block with a spring and they'll start talking about it, and then you'll be looking in life for a block with a spring and you'll never find one. You understand? I have gone into so much of engineering, I've never found this kind of an object, even in my machines. Let's be honest. You understand or not? It's not, it is just symbolic. He's telling you he's taking an object which is elastic when he takes a block with the spring. Okay? That means that you can deform it. Fair enough. Understand a few things first before we really get into the discussion. So we start our discussions with rigid bodies. That means it's a discussion which is an ideal situation. In real life, you might not find it. You can approximate, yes, this table looks pretty rigid, and you can approximate it. And you can say, all right, I'll treat this as a rigid body and I'll understand its dynamics. That's fine. But you must know where to draw the line. So we are discussing rigid bodies. Fair enough. And we are going to use this symbol for the rigid body. I might be talking of a chair or a table or a ladder or a ball. My symbol will be this. Okay, please understand this. It's only later on, when I become matured enough in understanding these laws, in understanding all the physical quantities, that means vocabulary words of physics, like different kinds of forces, and then terms like work, energy, and within energy, kinetic energy, potential energy, and then understanding momentum and change in momentum, understanding impulse, etc., etc. When I become very mature, then I will actually show a ladder the way it looks. I might actually draw a chair. You understand? But I'm just starting my discussions on the dynamics, and I'm going to just represent everything as a block. Okay, good. Oh, yes. Thank you. Because I've got on the other side donkeys, you know. They'll not tell me also if the quality of things not good. Okay, good. Yes. So fine, once we are through, let's now move on. Taken this object and kept it on a relatively horizontal ground. What's this? It's my rigid body. What's this? Could be a chair. What's this? Could be a table. Could be a ladder. You know, I know, everybody knows that if I give a push, or if I tie a rope and pull it, there is a very high chance that this object is going to move. If it's at rest, what do you mean? You're looking at an object, close your eyes, and then after a few seconds, open it. If the object is still there, what do we say? The object is at rest. That means its position has not changed. Okay, good. If I give a pull or a push, and if the object is at rest, it will start moving. What do you mean it started moving? There has been a change in its velocity. Initial velocity was 0. A change in velocity has taken place, which means it implies that there is an acceleration. We know that. Every time the magnitude of velocity changes, which is the speed, or every time the direction of motion changes, we say there is acceleration, correct? Good. So acceleration happened when we pushed or pulled this object which was at rest. This object, to start off with, could be having a velocity. To start off with, it has a velocity. We are clear what it means, right? It has a speed and it has a direction. Both together, we say it has a velocity. and I give it a push or a pull, I find that a change in velocity is taking place. Hence, there's an accident. So the object was moving, and then I just pushed it. Suddenly its direction changed, or even its speed changed. So we say that an acceleration has taken place. Now, can we connect these two? That with a push or a pull, you will see acceleration. Are you understand? This is exactly how Newton started his discussions. He said that these words, he told the scientific community that using a push and a pull is not good. I have a better word. I have a better word, force. And I want you to take this physical quantity just like when I gave you the physical quantity displacement, I told you it's a vector. I told you it has a magnitude and a direction. Similarly, when I gave you the motion vector, which was velocity, I told you it was a vector. And then when change in motion took place, I gave you acceleration and I told you that's a vector. Similarly, now I'm giving you a physical quantity, force. It's a vector. Capital F with an arrow on top, which says force has a magnitude and it has a direction. Fair enough. So he says this pushes and pulls. He told the scientific community, don't use these words. Just say you are applying a force. Good. So he says, I applied a force on this object which was at rest, and I saw it going through a change in motion, hence it had an acceleration. So he says, does it mean that force and acceleration have a connection? Does it mean that the force and acceleration have a connection? Now, this is where your teachers make a mistake. Okay. No, Newton said, it doesn't have a connection. Look at this object. To you, it appears at rest. You can't see a lot of forces which are already acting on it. This is on the ground, and the ground means the big earth. And all of us know, and all of us experiences on a daily basis. Like right now, I'm experiencing it. I'm trying to jump, but I'm being pulled down by this earth. I'm stuck to this earth. So is this chair, so is this table. The earth is holding all of us back by this force, which we will get to know and understand it better after a few chapters in the chapter of gravitation. For the time being, let us accept that this big planet on which we are standing is exerting a massive pull on us and is holding all of us to the earth. Even if I throw a ball, sooner or later that ball has to come back onto the earth because it is experiencing this force. Okay? So this object is experiencing that force, which normally we will represent as this, and we will call it the gravitational force. I'm not explaining you much, I'm just telling you something else which I was trying to explain, that there is no connection. Sorry, this is The question asked was, is there a connection between force and acceleration? The very first thing I told you is no. I'm trying to explain it. So there was already this force existing. Then the ground is pushing this object. Let us call that force N. Some normal force. So these two forces were existing, but the object was at rest. There were forces, but the object was at rest. There was no acceleration. There was no change in motion. So it is wrong to say that force is connected with acceleration. No. It is the resultant force. This is the mistake which often students make. It is the resultant force. It is the net force. If the resultant force is 0, then if the object is at rest, it will remain at rest. What does that mean? So many forces were there, including the wind force, maybe. The resultant means the sum of all these forces. When I added it vectorially, using an algebra called vector algebra, I found that the resultant was coming out 0. To start with, this body was at rest. It continues to be at rest. If the body was in motion, and when I added up all the forces, they added up to be 0, then this object, to start off with, it was in motion, it will continue to be in motion with the same speed, in the same direction. There is still no net force in it. It was initially moving with a certain speed and in a certain direction, and because all the forces added up to 0, it continued to move in that original direction with the original speed. Understand? But if the net force is non-zero, that means there is a resultant. Now comes the acceleration. Because the net force, when we added all the forces, today I'm just showing you two, I mean right now, but all the forces that the environment exerts on the object, when I added all of them, I found that there was a resultant. It was not 0. Then if there is a resultant, then if the body is at rest, then it will go through a change in motion, and hence there will be an acceleration. So Newton said that the net force has a connection with acceleration, not force. Only if the addition of all the forces comes out to be not 0, then we say that this net force now is connected to the acceleration. And he found that there was a direct proportionality. What do you mean by that? The direction of the net force and the direction of acceleration was the same, number one. And the magnitude of force was proportional to acceleration. Acceleration got doubled, force got doubled. But the directions were the same. Let us see it a little more in detail. But don't forget, don't ever say force is proportional to X. It's a horrible statement made by most of the school teachers. Okay. Now, let's move a step further. That I had this force, I called it something called Fg. I had this force, I called it M. There was a wind force. And when I added these up, I got the body initially at t equal to 0 was at rest. And suddenly some wind force started. And I noticed that a change in motion. Don't say change in velocity, because it doesn't give you any message. Say change in motion, change in the speed, change in the direction. Always keep saying that. Change in motion, I noticed. Maybe the speed changed. It was 0 initially, it's got some speed in meters per second. Maybe suddenly I noticed it started turning around, direction was changing because of this. That means it implies that, don't say equal to, it implies that there is an acceleration. Then I was sure that that means there has to be a net force. There has to be a net force which is not 0 acting on this object. All these forces are forces which the environment exerts on this object. We call them external forces. So that means the sum of these external forces came out to be not 0. That means there was a resultant. That is the reason why there was a change in motion. That is the reason why there was an acceleration. And I know from what Newton told me that this net force in direction and in magnitude, they are proportional. There is a direct proportionality. Good. Now, having explained this to the scientific community, then Newton said, let me take this object and let me keep changing the wind force. When only these two were there, the net force was coming out to be 0. But when the wind started blowing, now when I added this, this, and this, I found there was a net force. Let's call that net force 1, the resultant. Then I found that corresponding to this, there was an acceleration A1 for this object. Then I changed this to 2. I found that when I added up all these forces, there was a resultant force, which I call 2 now, and I found the acceleration to be some A2. Same object. Similarly, I changed this again, and I found F net 3 equal to A3. In direction, proportional. In magnitude, proportional. Then Newton took the magnitude of the net force and divided it by the magnitude of the acceleration. So net force 1 net force 2. To his surprise, he found they were equal. And they came out to be some number. He gave it a symbol M. Different resultant force, giving you a different acceleration, but the ratio was giving him the number M. When he changed the forces and he got a resultant which was something else, and hence its corresponding acceleration, when he again took the ratio of the magnitudes, he got the same number M. So he says, this M has nothing to do with the forces and nothing to do with the acceleration. This M has to do something with something that I have not changed. I didn't change the object. It has to do with the object, this number. And he gave it a beautiful name and he called it mass. And then he immediately added in his notes that this we will call it as the property of this rigid body. Don't use the definitions that your teachers have given in school, that mass is quantity of matter. It's a totally wrong statement. Newton never said it. Your teacher said it. Or some donkey who wrote that book said it. If you go back into the old notes which were written by Newton, for him, he said, it's the property of this object. And he made another statement. So, are we clear? Yes, we are clear. Proportional. When we remove the proportionality and we balance on the left and the right, after taking the correct measurement units, which we will define, when we balance the left and the right, the number M balances out the left and the right, and the number M balances out the left and the right. Then he defined this M to be connected with the object, and he called it mass, and he says, that's the property of this rigid body. He further added that it's an intrinsic property. It's an intrinsic property. What do you mean by that? This chalk, rigid body. I break it up into pieces. I catch hold of the smallest piece, I break it up, it breaks into smaller pieces. I break that up, it breaks into smaller pieces. I break that up, and now I have reached a stage where I'm now further breaking it. I'll be breaking it into pieces which I call molecules. Then I break it further, and I'll be breaking it into what I call atoms. And then I break up the atom, and I go into the atomic particles, and I still find this property there. Those atomic particles also still have the property mass. That's what we mean by intrinsic. You can't get rid of it. However small, you break particle, go down, atomic, subatomic, further break up those protons which you find in the nucleus, or those electrons, break them up into particles called quarks, you will still find they have mass, this property mass. That's what you mean when you say the property is intrinsic. The entire chapter of mechanics is developed on this intrinsic property mass, Newtonian mechanics. you will realize that once you start focusing on the right things. This will be totally covered in your 11th class. And then anywhere in the world, if you're doing physics, the initial beginning stage of physics covers that area called mechanics, which is nothing but based on the intrinsic property mass. Then the second half of physics is covered based on the intrinsic property charge. Same thing. I take the smallest particle and I will find that there is one more intrinsic property which I cannot get rid of, that is charge. And this entire second half of physics, which is called electromagnetism, where you discuss electrostatics, electric fields, magnetic fields, electromagnetic inductions, electromagnetic phenomena like light waves, all that, you'll be shocked, is because of this intrinsic property charge. There in your bulb, when I switch on the bulb, you say, oh, light. There is an electromagnetic wave which is coming out of that bulb. If you go deep into that bulb to find out who generated this electromagnetic wave, you will find that there is a charge which was oscillating inside. Millions of charges are there. But if you go specific to find out which source has given out a specific electromagnetic wave, you'll find that that source is charge, that intrinsic property. I will give you an example. If I keep charge here, static, let us say you know what is charge, let us say. And let us say a little bit of science has told you there are two kinds of charges, positives and negative. Let us say that if I'm holding the charge here, I can't hold it in my hand. I will be taking an object. This object has got millions of charges, millions of electrons, millions of protons, but they are balanced. So in physics, we say this body is not charged. Okay? But if I put little charge, excess charge on it, now I say the chalk is charged. Okay? Now this chalk is at rest. I find that because of that property charge, that excess charge there, the environment around has suddenly changed. You understand? When I check the environment, I find that there is an electric field in the environment. Some property, which I will explain later on when we move into the later half of physics. And now, I say fine. Now, I take this chalk and I start moving it. That means the charge is moving. Now, I check the environment around. To my surprise, I find magnetism, magnetic fields. There were only electric fields. Now I find magnetic fields. And this moving charge, I define as current. See? That means the charges moving in the wires in your house are creating in this environment here a magnetic field and electric field. Okay, now come back to the chalk. Now I take this chalk, which has the charge, that means I'm taking the charge, and I oscillate it. Now I go and check again the environment. There is an electric field, there is a magnetic field, but there is something shocking. I find there is an electromagnetic disturbance, and I find there is an electromagnetic pulse, and I find there is an electromagnetic wave. See what all this charge has created. The entire chapter. When somebody says, oh, There is magnetism around. That means you have to look for a charge, which is in motion somewhere around, which is giving rise to the magnetic field. And if you accelerate this, when I say I'm oscillating it, that is the easiest way to accelerate any particle. Okay? There's so many ways. I can take it in a circle, it accelerates, or when I oscillate it, it accelerates. The moment you accelerate a charge, you will get an electromagnetic pulse along with electricity, along with magnetism. You'll get an electromagnetic pulse also, which is, if it falls in the visible range of your senses, your eye, you will say light. If it doesn't, it just passes by. You understand what I mean? Understand this bit. If you understand physics the right way, you will enjoy it. So we will always focus on this intrinsic property mass. It is this property mass which is going to give rise to all the things that we experience in mechanics. You will see that. Because if this object, this rigid body, had no mass, then you wouldn't be able to apply the Newton's laws. You wouldn't see any kind of dynamics. That's how we see it. So now, when I say that I'm discussing the dynamics of rigid bodies, the moment I say rigid body and the moment I draw this thing, I will immediately write M there. That I'm talking of a rigid body which has an intrinsic property mass. Now, Newton looked at it the reverse way. He says, if you have a rigid body which has an intrinsic property mass, then if you apply a net force on this, you will see acceleration. Are you understand? See, now he speaks in a different way. But we know what it is. We know that when he says he applies the net force, that means there are the forces, but he's applying an external force, which, when all forces are added up, gives him a resultant force. And that resultant force, if it is not zero, will result in a change in motion, and hence we say we experience an acceleration. The object experiences an acceleration. We remove this proportionality and we put a number there. All physical quantities in physics, all over the world, we use the international system of measurements called the SI system, because in French it is something system international, whatever. The international system. Their mass is measured in kilograms. Just like distance, when we started our discussion, was measured in meters. Time was measured in seconds. Now we say mass is measured in kilograms. With the mass in kilograms and acceleration in meters per second square, all those units put together, Newton gave it a more compact kind of unit in the SI system. He says if that is equal to the force, the net force, then to pay respects, Newton did. The other scientific community which was involved in physics, to give respects to Newton, they called the unit of force in the SI system newtons. So next time when I say I'm applying a force of 10 newtons, you'll understand that that's the international system of measurement of force, and that is connected to all this. Fair enough. Now let us move further a step so that we further equip ourselves with the discussion. I'm taking an object, resting it on the ground. Please understand the symbols that I give. 2, 2. This is the symbol for the ground. So I'm taking an object, resting it on the ground, and I added up all the forces which were there, which I'm not showing. And I got the net resultant force in this direction. To my shocking surprise, I decided to apply the Newton's laws. Where Newton said that the net force will be proportional to acceleration. So if there is a net force, there has to be an acceleration, yes. And the direction of the net force and the acceleration have to be the same. So I expected the acceleration to be in this direction. Which means what? What does acceleration mean? Change in motion. I expected it to be in this direction. The body was at rest initially, and then I created a situation where the net force now was acting in this direction for the body which was at rest. Then this body should experience a change in motion in this direction. But to my surprise, which you, me, all of us can experience, I'm applying this force in this direction, but my object is moving in some other direction. I found the change in motion taking place in this direction. That means there's something not okay with this law. And Newton said, well, if you want to understand the dynamics that you are seeing now with your eyes, then you must understand one thing, that this is a vector force. You can resolve it. Net in the x direction. You can resolve this in the y direction. You can resolve this in the z direction by superimposing the Cartesian coordinate system, which is your x, y, z system on this. Superimpose it. Y, x, z. All three. And now he says, what are you going to do? You resolve. When you do this, you put this symbol, it means you are going to break it up into these components. You resolve this. F net in the x direction, F net in the y direction. Good, he says. Because I'm in a plane, this is a 2D diagram. It's not a 3D diagram, it's a 2D diagram. Then you can just resolve it into two components, x and y. Now, he says, add all the forces in the y direction. Add all the forces in the y direction, you will find the net force coming out to 0. Add all the forces in the x direction. You will find it coming out not. Hence, he says, there will be a change in motion in the x. You will see an acceleration in the x direction. That is why he says, when you applied that force, you expected that object to go right into the table, but it didn't. It moved horizontally. See how easy. You were able to explain the dynamics by resolving the forces. learned this word, resolving a vector, resolving forces. We have discussed this. That I can resolve, that means I can break up this force into its components, and I know that this force, its magnitude, this is how we write, will be F net x squared plus F net y squared. Correct? Because we are breaking it up into two components which are right angled to each other. Correct? And using the addition of vectors which we learned, that gives you the result. So we will resolve. Understand? I have a very sophisticated, rigid body going through some dynamics. I'm not able to comprehend it. Then Newton said, then you resolve your forces along x and y, and then you add up all the y's and check. You add up all the x's and check, and you will get your answer. You will know exactly in which direction you will see the dynamics. Is it clear? Good. Let's move forward. If we go through the whole of mechanics, you've got a cold, you've got a cough, you've got everything, right? Yeah, so that guy is getting worried. So what you do is you sit a little separate. Hey, you come forward and you push your chair there far off, or you move on to that chair. You come this side instead of worrying about all the germs that guy is throwing on you. You are okay? Are you fine? No? What do you want? You want anything? You want a mask? You want something like that? You're fine, right? Okay. So there you are. Now, let's move forward. A lot of things we've gained. Quietly, we have found out that if there is a net force, you don't have to write the big word resultant, you can just write net. That if there is a net force, then there will be an acceleration, and I can connect motion to the pushes and pulls force by just doing this. Okay? Good. Then this became the Newton's law of motion. This became the Newton's law of motion. You will be surprised that I will keep playing around with this equation, rearranging it, doing all kinds of crazy things, and I will extract a lot of information from it by bringing about new physical quantities, work, energy. They all come from this equation. The concepts of work, energy, the concepts of impulse, momentum, all these terms that you can think of, which you come across in physics, in the chapter of mechanics, they are from this simple law, which connects forces to motions. What causes motions? This is a motion parameter, physical quantity. It implies acceleration, implies that there is a change in motion. So we are connecting motions to forces. If the net force is zero, there won't be a delta V. That means there won't be change in motion. So if the body is at rest, it will remain at rest. And if it is in motion, it will continue to be in motion without any speed changing or any direction. That's all. That's exactly what this explains. You understand? Good. Now, keeping this one side, I can even write a little more that I can break it up into its components along a conventional axis, x-axis, y-axis, z-axis. I can write f net x is equal to m into ax, f net y is equal to m into ay, etc. and z. What does it mean? That if I break up this net force into its components along the x and the y-axis, and if the net force along the x-axis is not zero, then there will be a change in motion in the x direction. If the net force in the y direction is not zero, then there'll be a change in the motion in the y direction. You understand? Understand this. This equation is equal to 3 of these equations. Let me write down the number 3 also. Z equal to m into az. So when you write this, you remember that it is equal to these 3 equations. Now, if this is 0, then there won't be a change in motion in the x direction. If this is 0, there won't be a motion in the z direction. Why? If this is 0, there won't be motion in the z direction. That means the body is at rest. If, to start off with, it was at rest. If it was in motion, then it will continue to be in motion. But there won't be an axation in the x, y, or z. That means there won't be any change in motion. I think it's pretty clear. Good. Good. With this in mind, let us collect a little more. It's quite obvious that if I'm going to change the mass, things will change. For the same net force, listen to me carefully. I'm changing m, means I'm changing the object. Okay? But for all the objects, all the rigid bodies, I'm applying the same net force. Then can I build up a relationship between acceleration and mass? Yes. For the same net force, if the object has a big mass, then there'll be a small x. See? Inversely proportional. For the same net. Same net force I'm applying on object 2, which has a smaller mass. Its acceleration will be bigger. Are you understanding? Yes. So, for the same net force, resultant force, acting on different objects, then I can build up a relationship between acceleration and mass. They are inversely proportional. Big mass, small x. Small mass, big x. Is it clear? That is the reason why. That is the reason why. This is the Earth. It has a huge mass. And this ball has a small mass. Okay? When this ball is attracting the Earth, and the Earth is also attracting the ball, both of them are moving towards each other. Then, what is it? How is it that I am not experiencing the Earth moving towards the ball? It's because of it. The mass is so huge, that the acceleration is in micromillimeters per second. I don't feel it. For the same force, both are experiencing the same force. which is the gravitational force. You understand? But when I look at the ball, I can see the ball coming towards me at a fast speed with a huge acceleration because its mass is so small that I can feel the acceleration. But I don't feel it for this big planet on which I am. Are you understand? But basically both are moving towards each other. Where do I experience this? When I go up into space and when I look at the stars, that means the planets, there, when two big masses come close enough, they interact with each other, then I can see both of them moving towards each other very clearly. See? Now, because their accelerations are comparable, now I can see. You're not comparable. One is moving in micromillimeters per second square, say, or micromillimeter force is the same, gravitational force. Same force is acting. But the change in motion of the earth, that means the acceleration which the earth is experiencing is so small that I don't feel. I only see the ball moving towards it. Are you understanding? Yes. So there, this is an example of where the forces are the same, equal and opposite, but because the masses are so different, the experience of acceleration is different. All right? Okay. Let's move further. If you guys have any questions, you should just call out. I will go on. Because I have to clear everything before I really launch myself into the dynamics. I'll teach you today, I'll teach you tomorrow, I will move from one area to another area, I will develop new areas, I'll develop work energy areas, I'll develop impulse momentum concepts, I will develop so many things as I move. I'm developing the chapter of mechanics and I'll be taking different dynamic situations. Some of these dynamic situations which I see in life, collisions, explosions, I'll be able to explain slowly by using the impulse momentum concepts. Some situations I will explain using work energy concepts. As I move on and on and on and on, to my shocking surprise, I find two things. One, that this simple equation, this law of mechanics, this Newton's law is the controlling equation in all my analysis, in the whole of mechanics. The whole of mechanics is controlled by this. One. Secondly, I find that I can solve any problem in dynamics, whether it is in the chapter of rotational dynamics, whether it is in the chapter of collisions, or it is in the chapter where ropes and pulleys, etc. are involved, or it is in a chapter where I'm in a fluid and I'm experiencing all kinds of forces, buoyant forces, this, etc., etc. That all dynamic situations which I come across, I can explain all of them using 5 forces. Just 5. If you understand these 5 forces, if you understand how these 5 forces act, if you know how to represent them, and if you know how to apply them, you will be able to solve any dynamic situation in the whole of mechanics, which is 40% of your physics. Just 5 forces. I am tempted, though your books give you these forces one after the other, and they keep doing stuff and you lose focus. But we don't lose focus. we suddenly find, when we look at our entire mechanics, that, my God, it is only these 5 forces which are giving me all the answers. And the 5 forces, I would like to list them. We don't know them. We are going to learn them in this chapter, each one of them, but I would like to list them. The first one, because we are on this wonderful planet, the Earth, the first force that we all experience is the gravitational force. And we will use the symbol F, vector, of course, with a little subscript, small g. You understand? The small g indicates we are on the Earth. If we use F with the capital G, it means we are on some planet. This is also the gravitation. But we are not on the Earth. If we are on the Earth, we'll use a small g. If we are somewhere on Mars or in the moon, we're going to use F capital G. Okay? But it's the same force which we call gravitation. Now, let's, at this stage, we have not understood the chapter of gravitation, which is quite far off. But let us understand at this stage one, that all the objects that you see around, they all have this intrinsic property, mass. Okay? They could be having the intrinsic property charge also. But right now, I'm keeping charge silent. I'm only focusing on mass. Then, when you have 2 objects which have mass, and if you bring them close enough, suddenly you find they start gravitating towards each other. They start gravitating towards each other. That means now it's you are realizing that there is a gravitational force acting between the 2 objects, which is equal and opposite, which is now bringing the 2 objects together. This chair has a mass. I have a mass. Then how come I'm not gravitating towards the chair? Because I'm on this bigger mass, the Earth, which is not allowing me to move towards the chair. If the Earth was taken away, and if the chair and me were kept in space, then we would gravitate towards each other. Are you understanding? When I cut off the influence of the other planets like the Earth, then you take any 2 objects. This was an experiment carried out by Newton and his team, Newton and Cavendish, in a vacuumized space with very fine particles having masses M1 and M2, and he brought them close enough and he found that they start gravitating towards each other. He went to great extent, especially Cavendish, because Cavendish was an experimenter. Newton was not an experimenter. Newton was a theoretical physicist, but he had a brilliant mind, and he was able to interpret the results of different experiments being carried out by other people very well. And he was a Britisher. And Britain was ruling the world. So the Queen gave him audience. The Queen gave him all the powers. You understand? And so he had access to great publishing houses. He had access to all information coming from around the world. And he was able to interpret all those experiments which were being done in different countries, maybe China, maybe India, maybe Russia, etc. And he was able to make excellent abstractions and conclusions out of them. You understand? He had the advantage of being a British. There were many, many scientists from other countries who did wonderful work, but they were never given the importance. You understand? It was always Newton. Yes, Newton was a great mathematician. He was a genius of a man. But there were many other people during his time in the 17th and 18th century who unfortunately did not get the importance. You understand? Yes. So for us, it's fine. We got everything that was discovered that time through works which were done by Newton. Fair enough. Now, Newton made it very clear that 5 forces will be able to explain the entire dynamics of rigid bodies. The whole of mechanics can be explained if you understand these 5 forces. One is the gravitational force. We haven't understood it. We are going to understand it soon. The second is, he says, when 2 objects are interacting, that means, let us say, this book, I'm resting this book on this blackboard, okay? That means this book is interacting with the blackboard. When 2 objects start interacting, physically they interact by touching each other, or they interact from a distance because of certain forces, like one of them being the gravitational force, right? They could be interacting 2 objects. So he says when 2 objects, at this stage I will say, when 2 objects are in contact or they're interacting with each other. Now I'll say are in contact. Then there are 2 contact forces which he says you have to immediately become alert about. One is the normal force, the other one is the friction force. So how many forces have we come to now? Gravitational force, normal force, friction force. 3. Only 2 more are left. Number 3. If I tie a rope around this and I give it a tug, after the rope has become tensed, I give it a tug, then I will call that force the tension force. If the rope is slack, it's of no use, right? So I have to tense the rope, make it taut, and then apply the force, tension force, because this rope has to be always in tension. The last one is the spring force. Spring force, often called the Hooke's spring force. So how many forces are there? 1, 2, 3, 4, 5. Spring force is the same force when my object was having some elasticity. I had removed the elastic property outside, which now I am going to name this as the spring. There is a spring in my hand, which is giving it the elastic property. Deformation is taking place. When I remove the force, my object comes back to its original shape. That elasticity, that springiness, that spring which I connect to an object because the object is elastic, that will give rise to a force called the spring force. And there is one scientist, Robert Hooke, another Britisher, who was during the same time as Newton. He defined this force very well, so we call it the Hooke's force. You understand? And this is called the Hooke spring. Hooke. Okay? This is the Hooke's spring. And the force connected, when the spring is deformed, the force is called the spring force. These 5 forces, if you know how to apply them, where to apply them, when to apply them, whether it's this, or it's this, or it's this, or it's this, or this, then you know how to resolve any dynamic situation. Very good. Lot of stuff we are getting to know very fast, right? We don't have to read that book, which has so many pages. And I told you, dangerous books these are, right? They can injure you if they fall on your head, right? Have you shown Mr. Bushin that big book? Oh, did you get that book? You got G.B. Thomas? Looks very good. Did you cut it up into pieces? Why? That's crazy, man. You bought G.B. Thomas? G.B. Thomas. Your university. So my mother says, you know, we have to go to God. We have to go to Tirupati, because if you don't go to Tirupati, you will die early. So you say, okay, then pull out one chapter, roll it, put it in your pocket, you go to Tirupati. Because she's not going to allow you to take those big books, right? Tons of books. You cut up your book. And this binding costs nothing. See, table of content, chapter 1. So I take this book, go to Tirupati, come back after 3 days, chapter 1 over. When everybody is praying, I'm praying to my God. G.B. Thomas. I finished the chapter. I'm standing at a bus stand. I finished chapter 2. Soon the book will be over. But if you have to carry that book, whoa, you will never open that. How do you like the idea? Fantastic. When I was chopping that new book, my wife was shocked. Everybody was shocked. But I was happy my son was not shocked. He says, Dad, what a fantastic idea. And he cut up all his books, all his school books. Just have to cut it with a knife. Buy a new book and start cutting it with your knife and look at your mother. Don't you like the idea? Now, are you going to say why? Cut your books and stop worshipping books like a donkey. That is done by an uneducated man. He worships books. What are books? It's just printed stuff. You cut it up and you bring it to a convenient size so that you can use it. You understand? I find some shocking things around my place in Vizag. People buy a car and then they worship the car. They break a coconut, they do all kinds of things. What is it? It's a machine made by a man. It's nuts and bolts. Nuts and bolts can fall off. What has God to do with that? Correct? Some donkey who has assembled that machine forgot to tighten one nut. Where does God come in? Please stop worshipping machines. Stop doing all these crazy things, man. This is a very crazy country. I've noticed that. They worship anything that they find good. They'll sit outside the house and they'll start worshiping. Hey, Babu, what's happening here? There'll be a guy also who comes from some place and he will break a few coconuts. What are you doing? It's a house, man. I can change the architecture of the house anytime. You understand? Then you have people who come and do all kinds of vastu. Hey, Babu, toilet has to be here. If you don't shit in this corner, God is going to punish you. I mean, crazy things. Pragna doesn't like it because she's a godly person. Okay. But what I tell you is it's fine. Let your parents do it. Let the ancient people do it. But as you move on in life, and as you get into science, you will start discarding all these things, which are meaningless. And you will start reasoning out. And slowly, as you grow old, You might bring some God into the picture, but he'll be different from these gods. You understand? That's how it is. And I tell people, why don't you name your kid after Newton? Or why don't you call him mass? Or why don't you call him momentum? Or why don't you call him impulse? Imagine shouting out from your window, hey, mass, impulse. Your physics is getting revised. Instead of calling him, hey, Ram, Ram, or some Sham or something like that. I mean, understand this whole thing. We have discarded, you're a science student, you have discarded the gods of science. Then you can never do well in science. You understand? And I personally believe that even if we, let us say, with all kinds of spiritual these things, because being spiritual and being a physicist is no problems. Spirituality is, you know what? That in the middle of the night, lights went off, and I came out onto the terrace, and in that darkness, I looked up into the sky, and I saw this wonderful pattern of stars in the sky. I felt spiritual. You understand? That my God, my science couldn't have created this wonderful pattern in the sky. Are you getting me? That's spiritual. No, God in it, remember. So you can have spiritual kind of experiences in life, but don't connect all spiritual experiences with God. I think God can. You want a God? You really want a God? Then when you become 75 years old, look for a God. Then decide whether you want him to be a girl or a boy, and then pick up one God. You understand? And then subsequently, you keep looking at that God as you go blind and as you go deaf and things like that, and then you go off. And the best way is, supposing I am now old and I feel that, shit, man, everybody is saying I need God because I'm old now. Then you know what I'll do? I'll go off to the Himalayas, far off into the mountains, far off, isolate myself with all these materialistic things. And I will experience probably certain spiritual experiences, and I don't mind disappearing and dying. Yes. So I tell people, when they tell me they're going to the Himalayas, I say, what? Because when you go to the Himalayas, you're not supposed to come back to this horrible world. You understand? That's what they say. Are you understanding? Trying to take you away from all these religious strips you make. Okay, right, let's move. Let's move on. So we said, good. Let us now experience each force. Let us see whether we can create an environment where we can easily now know how to represent these forces. Let's take the first one. Now, I've come across physics papers, exam papers, when I'm correcting, and the guy has not shown the gravitational force. But he's wonderfully done the whole paper. I just cross the paper and throw it in the dustbin. How can you forget this force? That means you are saying you are not on this earth. Then where are you doing your physics? You understand? Never forget this force. You forget this force in mechanics or in physics, the examiner is going to punish you badly. Okay, number one. So this gravitational force, which we are now discussing, I will take different situations that you will come across. The best thing about this is you don't have to be in contact with the earth to experience. When I tossed the ball experienced this, which was in the air. I was on the earth, I also experienced. If I take the earth as this, very, very huge in size, in mass, everything. And if this chap is somewhere here on the earth, he is experiencing this force, which seems to be towards the center of the earth. Then, when I'm here, somewhere here on the earth, this could be an Australian, I'm somewhere in India, and I'm tossing this ball, then the ball is also experiencing this. So am I experiencing this. So is this bird which is flying experiencing. This force points towards the center of the earth. Then, when I, in my human scale, in my lab, outside in my physical world, when I took my rigid body, and when I wanted to show this force, I showed it like this. I did not bother to draw the curvature of the earth and show it at the center, moving towards the center. I just drew it exactly perpendicular to this horizontal flat. This is my world. This is my earth. My earth is not spherical. My earth in my scale is just a flat ground. But if I go up into space, a couple of 100 kilometers away, and I try to look down to the earth, probably I see the curvature. See? Because the radiuses are so huge that the curvature does not appear to me when I am at this scale. It just appears straight. For hundreds and hundreds of kilometers, it appears straight. I never see the curvature. You understand or not? You remember that. So I'm always going to draw the ground, and I'm going to show the gravitational force exactly vertically down, aligned to my y-axis always. Okay, now this is one example. Second example is, this is the wall. Now when I do this, so many sheds, it means it's a wall, all right? And I had some object, a big ball, connected by this some anchoring string, and it was resting like this. Okay, and this is the ground. Then if this has a mass m, then this is going to experience a gravitational force. And I'm just going to draw it like this. You understand? Straight down. I'm not going to go. Yes. No problem. No problem. This is going to be the simplest of the forces you can represent. But I was now on a mountain. I was on the slopes of the mountain. At our level, at 10 plus 2, the mountain is going to appear like this, sir. With this, I will say I am on an inclined plane. That means I'm on a mountain. And let us say I am here. This is the symbol. I am here. Then how will you show the gravitational force? You're like that. How will you show? Exactly vertical. Always vertical. Down. You understand? Exactly vertical. Perpendicular to any horizontal line you draw. Yes, you are on an incline, no problem. And when I kept the object here, I found it was moving. It was moving in this direction. There were no, let us say, any forces, and it was moving in this direction. Why wasn't it moving this? Resolve this direction and this direction. Then you find, yes, all the other forces were coming out zero, but this force was non-zero. That's why I saw the change in motion. I saw the acceleration in that. That we'll do later on. I'm just telling you how to represent the gravitational force. You understand? Yes, I understand. Oh, I had an object. There was a string connected, and it was going around what we call a pulley, and this was going there, and there was another pulley, and it was going there, and it was fixed here. The object of interest is this fellow who has a mass m. He wants me to understand the dynamics of this object. And the first force, gravitational force, I'm going to do this. Do I show the arrow from the center? Do I show it from it? Newton said that I have chosen the symbol this to represent a rigid body so that you don't worry about where to show them. Even if somebody shows it here, and somebody shows another force here, and the third guy shows a force here, it is understood. As long as it is touching this box, that it's acting on this box. It is acting on the rigid body. And honestly speaking, initially you realize that all of them are acting at a point. But if I was to draw this little dot and now tell you to show the forces, then how much time would it take? Oh my God, I have to see that the tail touches this. Oh yes, tail touches this. Oh, I should not miss this point. Instead of that, Newton said, finish. I box this point. You don't bother about it. Just draw a box and see that when you are representing forces, always see that the tail touches the object or the head touches the object. But if you are showing motion, then show the arrow, but never touch it to the object. Motion vectors. Never touch it to the object. Motion vectors. Never. The only arrows which touch the object are the forces. Is it clear? Never the motion arrows. If you touch the motion arrows to the object, you are conveying a wrong message to a physicist, and you are making your representation very shabby. Motion vectors are always just shown next to this, never touching the arrows. The arrows which touch a rigid body are one of the five forces or all the five, whichever are applicable at that, during that dynamic situation. Okay, what were we discussing? Gravitation force. It has always to be there because you're doing your physics and solving it on the earth. So we said the gravitational force, let us say with this much of knowledge, it's enough. Yes, it's quite enough. Let us now move to the contact forces. In the contact forces, you have the normal force and you have the friction force. This is something which is what will take some time for you. If there is no contact, these two cannot be there in your problem. If the body was hanging from a string, then the only force on this was the gravitational force, and because the string is there, there'll be a tension force, which I will explain you. But you can never have these two forces, because it is not in contact with anything. But the moment I have this ground, and I have this wall, and I have this rigid body, which is a ladder maybe, it is in contact here with the wall, then these two fellows have to be there. It is in contact here, then these two fellows have to be there. Then how do I show this fellow? Let us, for the time being, keep this silent. Let us say all surfaces are frictionless. That makes my problem easy. There is no friction. I haven't explained you what friction is, so I'm saying everything is frictionless, so I'm not talking about friction. Then this guy is always. What is he? He's a very strange force. What is it? Now you might say that, how did Newton know about these forces? Newton created these forces. He created these forces. He invented these forces to explain his dynamics. It is not that God told him, Babu, no, this forces. This is not God's force. This is created by Newton, Babu. Because tomorrow you will find some Baba sitting on the beach and saying, I'm getting energy. Energy was a word created by a physicist. God never talked about energy. But look at the way we have been trained in our mind. Hey, Babu, drink this milk, you get energy. Oh, eat this food, you'll get energy. Oh, go stand out in the sun, you'll get energy. See? But energy was a simple word created by a physicist. And if I go into the chapter of energy and I tell you how that word was created, you will have a real shock. That how these uneducated, half-baked Babas sitting on the beach talk about cosmic rays. I met one Baba on the beach. He says he has 4 dates every day. Dates, khajur. 4 dates every day. What else do you have, Baba? Air. What else? 1 glass of seawater. He said, it is enough to live. His pants were falling off. His hair had disappeared. I told him, it's enough. Unfortunately, he was passing by my house. It is just a coincidence that he got up from the beach and then he was passing by my house and he saw me standing at the gate. And he immediately came to me. My wife was on the balcony. And I'm talking to him as if we are friends. So, boss, how's life? And you understand? And he's telling me I have collected some bricks. I've collected some cement, which was donated to me. And I made one platform where he said in the forest. He showed me that some 50 kilometers from here, there is a forest where I made this. I'm going to make it into an ashram. I said, be very careful, if somebody sees you on that platform, they might come and kill you in the night. Be careful. So I said, what are you going to do? He says, I am going to all these villages which are around that jungle, and everybody is donating some rice, somebody is giving me some wheat, somebody is giving me something, and I'm collecting it there. And whoever comes there, I have one pot which is boiling all the time of water with the forest wood. And I put all these things in there. So there's always some rubbish being cooked there. Okay. So anybody who comes there, he removes with a spoon and in a bowl, he gives it. You understand? He says, already people in the villages are talking about this Baba who's giving very nutritious food. See, now he's spreading his great knowledge of those 4 dates and things like that. Now he's brought it to that. He was telling me that story. I told him, you must come. I said, I'm very busy with my physics. And he pushed me a little and he wanted to come in my house. So my wife was on the balcony. She shouted at him. So he moved back. Okay. I said, boss, you can't come inside. Babas are not allowed here. This is strictly no Baba zone. Okay. Babas, I can meet you on the road. I can meet you on the beach, but don't come into my house, please. My wife detests that. So he was so upset. Second day, I saw him going this way. So I was at the gate. I said, hi, Baba, where today? So he didn't look at me. He didn't talk to me. So I told him, what kind of a Baba you are? You told me you are not affected by all the people around, how angry they are or anything, and you will always smile and all. Today you're not talking. There is a devil in your house. He's pointing to my wife. I said, oh God, I'm telling you, when I hear these stories from these chaps, I'm actually frightened to say hello to any Baba around, honestly. Because try surviving on 4 dates, air, and 1 glass of seawater, and see what becomes. You'll stop looking like a human being. You understand? Okay, let's move on. But these are the kind of people you get. Tomorrow he'll tell me, sit your cosmic energy, and I don't know what all. You understand these half words which they pick up from here and there and they use it. And there are so many uneducated people in this country that he'll always get followers. He'll always get somebody when he looks up into the sky and says, see that star? Watch that star every day. And those poor villagers will be watching it every day, and then he'll give some prayer to it also. That's why I'm too scared of this, all these, things like all these Vastu business guys. Okay, let's move on. So, the contact force N I'm talking. Now, how do you draw this N? There is a corner, there's a straight line, and there is a corner. Please pay attention. These are very important. And there is this corner, right, of this resting board. How do you show the normal force? Because my fellow of interest is the ladder, not the wall. So I'm going to show all the forces on my ladder. Then how do I show it here? Look at the contact surfaces. There is a corner, there is a straight member. Look at the straight member and draw a force normal to that. Draw a force normal, not on the wall, on the object. See? So I drew that. So I will draw a force N, and that will be 1. Why? Because there's going to be another normal force. I looked at both the surfaces. Whichever surface is straight, I will draw the normal to that. Listen to me carefully. So this surface was straight, which was in contact with this. I draw the normal. Never, never, ever call this N and call this N. How do you know they are of the same value? Always say N1, N2. Big mistakes people make. And everywhere. And then somewhere they'll be adding up all the N's. You understand? This is different surface context, isn't it? Okay, now, second one. I am on a hill. This is the ground, inclined. And this is my object. Then I will look at the surfaces in contact. This is this guy's surface and this is this guy's. Both are straight. Draw a normal to that. Always as if the ground is pushing this up. Always as if the wall is pushing this ladder out. Are you understanding? Normal, normal, perpendicular. Am I clear? Don't make that mistake. Or come here. I have a pillar. I have another pillar. And I have a slab on it. Then contact. See, two surfaces. This is straight, normal. Because this fellow is of my interest, not the pillar. Normal. And one. Come here. Contact. Straight. Normal. Are we clear? And two. Don't call it NN. Now see what I'm doing. Please pay attention. I'm giving you some situations so that, just give me another minute, please, guys who are online. Some situations so that I can start taking some dynamic equations fast after I explained you some more forces. Where are we? All frictionless surface. There's no friction, so I'm not showing this contact. I'm only showing this contact. Soon you'll find both these are connected. There is a wonderful relationship between the two. Okay? But for the time being, Newton broke up the contact force into two. And he explained us how to represent each one of them. I am not showing friction because I'm saying everything is frictionless. I'm only showing N, which is a contact force. Only if there's a contact you show it. Pillar. The slab was such that the corners met. Pillar. You will come across situations, corner. Now, which one is straight? Pay attention. Then, this is the object of my interest. Then, how do I show it? Well, you show a force this way, N1, and you show a force this way, N2. Are we clear? 2. Yeah, straight, N3. Are we clear? Corner to corner. Surface there. Surface there. Contact is corner. You show 2. Next. Just hold on for a second. This is normal, our steps, getting down the steps. And I have a ball, okay, touching ball. Then contact. Contact is there, contact is there. Look at the straight surface, not the curve, all right? Straight. Draw the normal. But when you draw the normal, when you have a tangent, and if you draw the normal, it will go through the center, always. If I have a circle, and if I draw a line which is exactly tangent, and if I draw normal, it will always go through the center. That's a property of a circle. So, normal from here. You can draw from here like this, or you just show like this. Similarly, here, contact. Straight, draw normal to this surface. Are we clear? This is how Newton explained his forces one by one, all the 5 forces in his books. And this is what I expect your teachers to do. Once 5 forces are clear, then you throw a problem. And see how the students are representing the forces, how they are adding up the forces. And if they add up and they get a net resultant, then how the acceleration will act, how the dynamics will take place, in which direction the body will start moving. The rigid body. Is it okay? It's so simple, right? We'll continue our discussions. We are in no hurry because we are covering a lot of ground, because we are not reading matter which is unimportant. All right? Right. We'll stop here. Any questions that side, please? You are